Today in the workshop, we'll be controlling DC gear motors using pulse width modulation. You'll learn how using MOSFETs and increasing the PWM frequency can offer improved performance. I've also got a special announcement for you today, so stay tuned and welcome to the workshop. Hello and welcome to the workshop. Now before we get started on today's video, I would like to make a couple of announcements, and basically the announcements boil down to the fact that you're going to be seeing a lot more of the DroneBot workshop, and I hope that's a good thing. Now starting today, there's going to be a DroneBot workshop episode every weekend, every Saturday. So these are the full-sized episodes that you've enjoyed for the last year and a half. They'll be coming to you every Saturday now. But in addition, there's going to be a second series of videos, and these videos were inspired by one of the comments that one of you made on one of my videos that said, have you ever thought of building a real robot? Well, the answer to that is yes. I've thought about building a real robot for over 40 years now, but now is the time to do it. So what I'm going to do is a second series of videos on building a real robot, and you will be seeing those videos every Thursday. Now these videos won't be as long as my normal videos. My normal videos are a half an hour to 45 minutes long. These will be more like 10 or 15 minutes long, but it'll take you step by step through the process of building a full-sized robot that has a lot of capabilities. So I hope you will join me for that. So on to today's episode, and today's episode has to do with the robot because we're going to be working with the motors that I'm using on this robot, these large DC gear motors that I have mounted on this frame. Now controlling these motors is a little more difficult than the motors we've used on the small robot cars. For those ones we've used an L298N, and the L298N is a great module. It's an inexpensive 8-pitch bridge, and I've used it for so many projects, but for this project I can't use it. It doesn't have the current capability. It doesn't have the efficiency. So I'm going to show you a different motor driver that we're going to be using. I'm also got all the test equipment out here, as you can see, because what we're going to do is experiment with pulse width modulation. We're going to experiment with different frequencies and find out if we can improve the performance of the motors. We're going to give it a load test with a very large load and try to get the most performance we can out of these things. And so we've got a lot to cover today. What we're going to start off with is a bit of a refresher on how an H-bridge works, and I'll explain how this new H-bridge I've got is superior to an L298N. So let's get going. So let's take a quick look at H-bridge design. As you may recall, an H-bridge is an arrangement where a DC motor is connected to a power source using 4 switching devices. When 2 of the switches are thrown, current flows through the motor. In this particular case, the motor is going to spin clockwise. Notice the polarity of the voltage across the motor. Now, if we throw the other 2 switches, you can see the current is applied to the motor in the opposite polarity. In this particular case, the motor will spin counterclockwise. Now in real life, H-bridges are seldom built with mechanical switches, although you could make one that way. Normally, transistors are used instead of switches. The older style of doing this was to use bipolar transistors. As you can see, when 2 of the transistors are switched on, current is applied to the motor, just as it was with the switches. However, bipolar transistors have a voltage drop of 0.7 volts each, making the total drop 1.4 volts. This means your motor receives 1.4 volts less than the power supply voltage. We can replace the bipolar transistors with MOSFETs for improved performance. When the MOSFETs are switched on, they will apply current to the motor. However, the voltage drop across a MOSFET is very low, 0.1 of a volt or less, making the total voltage drop 0.2 of a volt or less. MOSFETs are a much more efficient way of designing an H-bridge. So I have here two H bridges, one which you're probably very familiar with, the L298N, and this is the H bridge I'm going to be using today, a Cytron MD10C. Now I wanted to compare the two of these for you. As you can see, they're both about the same width, and the Cytron is maybe almost twice as long as the L298N, but one really interesting thing is when I turn them on their side and compare them, you can see that the L298N is about twice as tall, and the reason for that height is the heat sink over here. Now, one interesting thing though is the L298N can handle a maximum current of about 3.5 amperes, and at that point this heat sink is getting very, very warm. This motor controller, the Cytron MD10C, can handle a current of 13 amperes continuous and can handle peaks of up to 30 amperes, and yet, as you can see, it doesn't even have a heat sink. What you've got over here are the 4 MOSFETs, and the real difference, of course, is because this uses MOSFETs and the L298N uses bipolar transistors, there's very, very little heat that comes off of this device. So let's take a closer look at the Cytron MD10C. The Cytron MD10C is a single motor H-bridge controller. The device uses MOSFETs for high efficiency. The MD10C is powered with a 5 to 30 volt DC power supply. This is also the power supply used for the motor itself. It can supply up to 13 amperes of constant current. It can also supply 30 amperes of peak current for a maximum of 10 seconds. The Cytron MD10C has a maximum PWM frequency of 20 kHz. Now here are the connections on the device. The screw terminals on one side have 2 connections for the power supply. Beside that are the 2 connections for the motor itself. The connector on the other side of the board has 3 pins. The dir pin determines the direction the motor will rotate. The PWM pin is where you input the pulse width modulation to control the motor's speed, and there is a ground pin as well. There are 2 push buttons on the board. These are for testing the motor in either direction. There are also 2 direction LEDs which indicate the direction the motor is currently turning. Okay, now that we've learned a little bit about the Cytron motor controller, let's start using it with an Arduino. Now, Cytron was kind enough on their website to supply some sample code. However, the sample code I found had a few problems with it. I liked the sample code because it made use of the LCD keypad shield. I've used that before on the video I did about LCD displays, and it's a nice device. It has an LCD display and a couple of push buttons, which interestingly enough work on the analog input of the Arduino, so it doesn't take up a bunch of digital I/O pins. However, the Cytron code wouldn't actually work. One of the problems with it is they were sending PWM signals to a pin that didn't even support PWM. Well, I rewrote the sketch and found that it had a few extraneous comments and statements that weren't really necessary. I think really it was adapted from some other project and thrown together, and again, I appreciate them supplying it, but I had to do a bit of repairs on it. So what I'm going to show you is the repaired sketch that will use the LCD keypad shield with the Arduino in order to control the motor via PWM. Now, this sketch also requires a library, which I found very difficult to get, but I eventually found that it's a library to drive the LCD keypad shield, and you can find that on the article accompanying this video. So now let's go and take a look at that sketch. Now here's how we're going to hook up our experiments. You are going to need an Arduino Uno, a gear motor, the Cytron MD10C, and a power supply suitable for the gear motor. I'm showing a 12 volt supply here. You'll also need the LCD keypad shield, which I'm not showing at the moment. We'll begin by connecting the ground pin from the Arduino to the ground input on the MD10C. We'll then connect pin 3 from the Arduino to the PWM input. Next, we'll connect pin 2 of the Arduino to the direction input on the motor driver. Next, we'll connect our motor to the A and B terminals on the motor driver. Now the power supply. First the positive to the positive input, and the negative side to the ground input. Once it's all wired, you can put your LCD shield onto the Arduino, and we're ready to begin our tests. Now let's take a look at the sketch we'll be using for our PWM controller. We start off by including 2 libraries for the display. First, the Liquid Crystal library, which is part of your Arduino IDE. We'll also include the LCD key library. You can download this as a zip file on the article accompanying this video on the dronebotworkshop.com website. Next, we define the key codes used on the keypad, and so they're defined over here. We'll define a pin for the analog keypad. This keypad uses a number of resistors to present a different analog voltage every time a key is pressed. So we're going to use analog input A2 because that's the one that's connected to them. The PWM output pin is pin 3, and the motor direction pin is pin 2. Next, we'll create an object called LCD with the connections to the liquid crystal display, which are as follows here. We'll also create an object called keypad using the LCD key library. We define an integer called PWM value. This is the actual value from 0 to 255 of the actual PWM being sent to the motor. We also define a variable that represents the key that has been pressed. In our setup, we set up the LCD as a 16-character 2-line display, and we clear the LCD, and we define a couple of the pins as being outputs. Now on to the loop. The loop happens in a while one statement. You may not be familiar with this, but this is a C++ statement that just means execute this continuously. First, we'll go and get the key that has been pressed, and based on the key value, we will do the following things. If the left button was pressed, this is what toggles the motor direction. So we'll do a digital write to the direction pin with the inverse of what that pin is currently at. So if that pin is a 0, we'll change it to a 1, and if it's a 1, it'll be changed into a 0. And then we delay for 200 milliseconds. If the up button is pressed, we want to increase the motor speed, so we'll increment the PWM value and then delay for 200 milliseconds and clear the LCD. The down button will decrement the speed, so we will decrement the PWM value and again delay and clear the LCD. We need to make certain that the PWM values lie in the range of 0 to 255. So we'll make certain that if it ever goes over 255, we'll just set it to 255. And if it goes below 0, we'll set it to 0. We use the analog write command to write pulse width modulation out to the output pin using our PWM value. And finally, we will display the results on the liquid crystal display. So now that you've seen our simple sketch, let's take a look at it in action. Now here's the test setup that I'll be using today. Let me walk you through what we've got over here. Now down over here, of course, I've got my Arduino with the LCD keypad shield. I'm using one of these shields underneath it that has screw terminals on it, and it's making it very easy to connect my jumpers up to the Arduino. Some of these keypad shields, not this particular one, but some of them also have pins over here, duplicating the pins on the Arduino to make the connections easier for you. Now, this little solderless breadboard is just where I'm interconnecting a number of things, grounds and leads, etc. And as I'll show you later, I can also use my signal generator up here instead of the Arduino as my PWM source. Now here, of course, are the two Cytron boards. I've got two of them, and they're just basically wired in parallel on the inputs. So the Arduino output is actually feeding the pulse width modulation of both of these, as well as the direction of both of these. These are driving the two individual motors, which you see up here on my frame over here. Now I've got my power supply back over here. That's just going to be used for powering up the motors and the boards, obviously. The display on the bottom, the power supply is in standby, but when it's on, the display on the bottom here will display the current, and that's going to be very useful for us. Now over here I've got a signal generator. As I said, this can be used instead of the Arduino, so I can do some custom PWM and also change the PWM frequency. We'll deal with that a bit later. Because the PWM frequency is going to come into play, I've got a frequency counter over here, and that's just so you can see the frequency of the pulse width modulation. And over here I've got an oscilloscope, and on the scope we'll be able to observe the PWM waveforms. If you can see the scope right now, and nothing's going through it at the moment, but if you can see it, the yellow trace on the top is going to be the PWM input, and the blue trace on the bottom is where I'm going to measure the output going to one of the motor coils, just so we can see the effect of changing the frequency, how it affects the waveform. So now that you've seen my test setup, let's run our first test. Alright, here we are for our first test of the Arduino motor controller. Now I'm going to hit the button here to change the direction of it, and that way on the bottom trace we will be able to see the output waveform. I'm going to start bringing it up. Seem to have a frequency of 488 Hertz, by the way, but I'm focusing on the power supply, so I want you to watch it. And as you can see, our bottom waveform isn't exactly perfect. It's got a lot of ringing and stuff on the top. However, it is working. The motor is spinning. Look at our power supply. It's getting very erratic, though. It's using almost an ampere now. Bring the speed up some more. That waveform in the bottom still doesn't look great. The top waveform, of course, is fine. That's the input from the Arduino. I'm going to go to 127. Now this should be a perfect square wave. It certainly is very nice on the top. On the bottom it's not. Look at that power supply though. Look at the way the current is fluctuating all over the place. I'll go faster and faster. Bring the speed up. Power supply is still going kind of nuts. Okay, we're approaching full speed now. There we are at full speed. Power supply is stabilized now. And of course there are no waveforms to look at because full speed simply means everything is being held high. And so our controller seems to work. A little bit erratic on the power supply, but otherwise it seems to be a working device. So our pulse width modulation demonstration seems to work pretty well. We're able to control the motor down to a very slow speed while still maintaining full torque. And that is, of course, the real advantage of using PWM with DC motors. However, one thing you may or may not have noticed is that at the very slow speeds, there is a very loud humming sound coming from the motor, and it's a bit disturbing. It also makes me think that the motor is perhaps not working at its full efficiency. What I want to do next is use pulse width modulation, but change the frequency of the pulse width modulation and see if I can get some better effects, see if I can reduce the humming and also improve the efficiency of the motors. Now, in order to do that, I've got a little test set up here, and I'll show it to you in detail, but essentially what I'm going to be using is a signal generator instead of an Arduino. And I'm going to be using the signal generator to generate a square wave whose pulse width that I can vary, and then we're going to test it at different frequencies and see if we can improve the performance of our motors by changing the PWM frequency. So let's go ahead, take a look at the test setup, and start doing that. So for this test, I'm now going to be using my signal generator to send out the pulse width modulated signal instead of using the Arduino. The Arduino is still in the circuit though, because I'm still using the direction output on the Arduino so that I can reverse the direction by either sending 5 volts or ground out to the direction pin on the motor controllers. Now if I had a separate 5-volt power supply, I could have used that instead and eliminated the Arduino, but I just wanted to let you know why the Arduino's still there. Now right now I've set this for 1000 Hertz, and I've got my power supply on standby, so let's turn it on. And the duty cycle right now is 50%, by the way. It's a square wave. And as you can see, the scope trace looks a lot nicer than it did. Now this is about twice the frequency that the Arduino's running at. And also, if you take a look at the power supply, it's not jumping all over the place right now. So raising the frequency seems to have a positive effect. Now let's just raise it a little more. Now we're at 2500. Let's just set this so you can see the waveform. Look at that waveform on the bottom. It's really, really nice. And look at the power supply too. We're only taking half an amp, so this seems to be a lot more efficient. See if we can get a little higher. We're now at 3000 Hertz, and the square wave that's going out is almost perfect. By the way, the rounding on the square wave going in is a bit of a farce. It has to do with my frequency counter loading it down. It's the probe on the counter. I haven't been able to get a good signal with it on times 10, and if I put it on times 10, I'll just do that for a second for you. As you can see, it cleans up the waveform. But as you could also see from the display, it gives an erratic display in the counter, so it actually is feeding a nice square wave in. But look at that square wave going out. Isn't that really nice? Now let's see if we can actually change the duty cycle on this over here. So right now we're at 50%. Let's go down 40%, 30%. So we're slowing the motor down. It was at the slow speeds we were getting that humming sound. It's nowhere near as strong, although there's a bit of a high-pitched sound because we're driving it at 3000 Hertz. And there, as we go down, now we're at a 20% duty cycle, 10%. The motors are still slightly turning. Look at the current, too. The current is really a lot less than it was before. Now we're at 70% duty cycle. 80%, 90% duty cycle at 3000 Hertz. The waveform on the output, the blue one, looks nice. I'm going to bring it down now again to 50. And the power supply, nice. So definitely there seems to be an advantage to raising the PWM frequency. So as we can see, changing the pulse width modulation frequency definitely has an effect on the sound that our motors make. However, what effect is it having on the motor performance? Now, one thing about PWM frequency is as the frequency goes up, sometimes the efficiency of the motor tends to go down. There's kind of a graph you can follow for that, and there comes a point where if you increase the frequency, you're going to really start decreasing the amount of torque that the motor can give. And of course we want this to be a high torque motor. That's why I bought these big motors, and they're going to have to carry a fair deal of weight around, so I want them to be able to do that. So in order to test this, what I've done is I don't have any scientific lab testing that can measure torque, but I decided to give it a real world test. And here's my real world test. I'm going to carry this around. Now, this is a 10 kilogram bag of road salt. Now, for those of you who don't live in winter climates, you may not be aware that in the winter we spread down salt and sand in order to provide traction on the ice, and the salt will actually melt the ice as well. And this is 10 kilograms. For those of you who don't speak metric, 10 kilograms is 22 pounds, which is why I'm straining a bit holding this thing. Now, we're going to put this onto the robot and have it drive it across the room. I'm going to start off at the same PWM frequency the Arduino used, 488 Hertz, and then we're going to move the frequency up and see how it affects the performance of the robot. So let me put this thing down and we'll get going with that test. Okay, we've got the 22 pounds, 10 kilograms of salt on the base, along with a board which probably weighs close to a pound in itself, and we're set to go. I've got the PWM set at 3000 Hertz, and as you can see the square wave over there, right now the power supply is on standby, which is why it's not moving. It's at a 50% duty cycle, so it should go at half speed. And I've only got a little space over here I can test it in, but it should be good enough to see if we can at least move the motors. And here we go. And it seems to move rather well. Let me reverse it and try it again. Reverse. And it looks like it works pretty well. Like, it has no problem carrying 10 kilograms of load, plus that board, plus its own weight. So it's pretty high torque. I would say we have no problem at 3000 Hertz moving everything around. So it looks like there's some definite advantages to raising the frequency of our pulse width modulation, but of course I don't want to use a signal generator in my final design. I want to use something else. I specifically would like to use an Arduino, but the Arduino doesn't seem to have a method of changing that frequency, or does it? It turns out it does. The Arduino's pulse width modulation frequency is determined by a timer inside the Arduino, and there are a number of internal timers in the Arduino. And different Arduinos, like the Arduino Mega, also have additional timers. Now, these timers determine the pulse width modulation frequency. They also control a number of other things, such as the delay function, the tone function. So if you start changing the values on the timers, you need to be aware that some of the other functions, like delay, tone, servo, may be affected by those changes. Now, you can change the PWM timers. Some low-level code will actually allow you to change the divisor on the timer. And the divisor divides the clock signal, the 16 megahertz clock signal in the Arduino, and it divides it down to a specific frequency. And I've found a function that lets you change those timers. I found it up on GitHub. So I'm adding that function to my code to see if I can raise the frequency of the pulse width modulation on the Arduino. So let me show you that code right now. Now here's our sketch for running the pulse width modulation at a higher frequency. Now this is basically an identical sketch to the one we just looked at, with one addition. There's a new function in here called set PWM frequency, and this function came from a member on the Arduino forum. It was contributed by someone called MACEGR. Now, again, this is an identical sketch, so I won't go through all of the details with you because we've done that already. I just want to show you the set PWM frequency function. You'll find it down at the bottom of the sketch over here, and you'll notice that it has two inputs. The pin number, this is the PWM pin that you want to change the frequency on, and a divisor, the amount you want to divide the Arduino clock frequency down to use, and this is what changes the PWM frequency. And so all that we need to do in our sketch to add this is in the setup, we'll use a set PWM frequency command, we'll call it, we'll pass it the pin, which has been represented by the variable PWM, and we're going to divide the master clock by 8. And so basically, again, the same sketch with a higher PWM frequency. So now let's take a look at it and see the difference between it and our previous sketch. So now let's test out our Arduino driver with the higher frequency PWM. So I've set the direction to 1 again so that we can observe the output trace on the scope as well as the input trace. And let's start bringing the speed up. As you can see now, our frequency is 3909, and our motors are starting to move. Looking at our square wave, we seem to have a very nice one. The width is getting bigger. Let's get up to 127. So we've got a square wave over here going in, and a very nice looking square wave going out as well too. And we're consuming about half an amp right now at half speed, and this of course is for both motors. Bring the speed up a bit more. As you can see on our scope, the pulse is getting wider. And we're coming up close to full speed now. Here we are, full speed, and of course the frequency counter is dropped out because there is no frequency. We are completely high right now, so the motor is constantly being turned. And we'll start bringing it down again. So that seems to work pretty well. Okay, let's give this a test with our Arduino using the high frequency PWM. Now, I've got the Arduino set for the direction 1, so it should go forward when I activate the power supply. As you can see, the frequency is 3910, so that's the frequency of the PWM now. And on the scope, as you can see, we have a nice square wave. So let's see what happens when we activate this. Very nice. I'll reverse it. By the way, the reason I don't reverse while it's running is I keep dropping the bag of salt off of it when I do that. And here we go. I'll reverse now. What I'm going to do now is bring the speed down. So if you take a look at the scope, you can see the pulse is getting narrower. I'll bring this down to about, I don't know. This is 80. 80 out of 255, that is. So the direction is forward. And as you can see, it can roll. Maybe I can reverse that without dropping the sandbag. Maybe. There we go. And a low speed is a very good test for the torque, because of course the motors aren't getting power all the time. And as you can see, it seems to work pretty well. So I think this is the frequency that I will use in my Arduino PWM controller. And if you look at the power supply too, look how efficient that is. Those are 2 motors there, by the way. Well, alright, that about wraps it up for today's video. I'd like to thank you for joining me today. Now, if you need to get the code or the libraries to duplicate what I've done, you will find all of that on the article on the dronebotworkshop.com website, and there's a link to that article right below this video. When you're on the website, could you please subscribe to my newsletter if you haven't done that already? The newsletter is not a sales letter, it's my way of keeping in touch with you to let you know what's going on in the workshop. And as you can see, there's quite a bit going on in the workshop. It also lets me get feedback from you as to what subjects you would like me to cover on the DroneBot Workshop videos. Now, as I said at the beginning of today's video, there will be a new video every weekend, as well as a video on Thursday covering the robot project, and I'm hoping you'll join me for that. If you haven't yet, please subscribe to the YouTube channel. I would really be very grateful if you would do that. Until next time, take care of yourselves, and I hope to see you again very, very soon here in the workshop. Goodbye for now.